Welcome to Module 3 of the Megget Sensing Systems Industrial Vibration Training course, Measurement Types. In this module, we will cover overall measurements, time waveform measurements, FFT or spectrums, phase, and specialty measurements. Overall vibration measurements are a calculated value representing the amplitude over a given period of time. It is represented numerically and often trended over time. Overall vibration measurements can be expressed in one of three ways. Root mean squared, or RMS, which is the average energy. Peak, which is a measure of either the highest peak in the positive direction or the highest peak in the negative direction. Or peak to peak, which is a measure from the highest peak in the positive direction to the highest peak in the negative direction. There are two types of overall measurements, an analog overall or a digital overall. With an analog circuit is used to detect the peak vibration level, typically prior to digitizing the signal. There are two common methods for this, RMS with the derived peak value or true peak detection. For digital overalls, the calculations are performed after digitizing the signal. They are often calculated from the vibration spectrum. This is an additive value. A frequency range of interest can usually be specified, and the overall is limited to that range. Overall vibration measurements from different equipment do not always match. This is because there are multiple methods for calculating the overall vibration. Some equipment will measure the RMS value and then multiply it by a known factor to get the peak value. Others will measure the peak-to-peak value and divide by 2. The overall values will only match if the exact collection, calculation methods, and bandwidths are used. In our example, the peak value is very similar, but the RMS value would be very different. This is what leads to differences in overall values. Vibration severity can be a difficult thing to determine. Fortunately, ISO has a standard which you can use as a starting point. The ISO 10816 standard classifies vibration severity based on the speed of the equipment, the way it is mounted, and the vibration levels. A time waveform is a representation of the amplitude of vibration over a period of time. Amplitude is a representation of how much energy is present. In our example, the red and blue graphs represent different amplitudes at the same frequency. The amplitude represented in red is much more severe than the one in blue. It is important to understand the relationship between amplitudes when measured in different ways. Vibration can be measured in acceleration, velocity, or displacement. While each has its own merits, the same vibration data can seem very different. Displacement accentuates lower frequency events and is often used for things like balancing when we are only interested in rotational speed. Acceleration accentuates the higher frequency events and is commonly used to provide early detection of bearing problems and lubrication-related problems. Velocity is the most commonly used and is good balance when looking at most frequencies except at the upper and lower frequency extremes. Frequency is defined as how often an event occurs over a given time period. In the world of vibration analysis, frequency is typically expressed in two ways. Hertz, which is equal to cycles per second, or cycles per minute, CPM. 60 CPM equals 1 Hertz. The frequency of repetitive events can be calculated using the following formula. Frequency in Hertz equals 1 divided by time in seconds. In our example, the frequency of the blue event is calculated as F equals 1 divided by 1. So our frequency is equal to 1 Hertz or 60 CPM. The frequency of the gray event is calculated as frequency equals 1 divided by 0.2. So our frequency equals 5 Hertz or 300 CPM. There is a distinct relationship between frequency, amplitude, and time. If we look at a complex time waveform, we see that many frequencies of different amplitudes combine to give us our time waveform over time. A digital time waveform is created when we convert the analog signal from an accelerometer to a digital signal. To digitize a time waveform, we use electronics an ADD converter, to sample the analog signal. Sample rate is what determines how many points of digital data are used to represent a given period of time. The sample rate needs to be at least 2 times the highest frequency of interest. Let's take a look at an example of sample rates. In this example, there are 2 frequencies represented in the graph. One a lower frequency, represented by the blue line, and one that's a higher frequency, represented by the gray line. Let's first look at the low frequency example. Below is a representation of the low frequency with an appropriate sample rate. The sample rate reasonably and accurately represents the signal in a digital form. Next, let's look at a higher frequency example. If we apply the same sample rate that we did with the lower frequency example, we will get a misrepresentation of the signal. The blue squares represent the samples. Higher frequency events require a higher sample rate to accurately represent the signal in a digital form. If we look at the stored data for our example on the left, you can see that the digital time waveform, when created with too low of a sample rate, does not accurately represent the actual vibration, which is the gray signal on the right. There are typically user-defined settings in a data collector that determine the lowest and highest frequencies of interest, or Fmin and Fmax. It is important to understand sample rates because they are often linked to Fmax settings in a data collector. A higher Fmax typically means a faster sample rate. A lower Fmax could mean a lower sample rate. The wrong Fmax could lead to not seeing the true vibration energy. Some data collectors have a limit to the number of samples that can be stored with a digital time waveform. The data seen during the measurement may not be the same data that you see back at the computer. It can be particularly challenging to monitor slow-speed running equipment when high frequencies of interest are present, such as gear mesh or fluting. There may be trade-offs when optimizing the Fmax, sample rate, and stored data points. All of our examples so far have been simple time waveforms. These waveforms have been simple and periodic, but this is not representative of most machines. A complex time waveform is what you are more likely to see. It is made up of multiple frequencies such as running speed, gear mesh, and bearing frequencies. It can appear non-periodic. The multiple individual frequencies combine to create the complex time waveform. There are some faults that will only show up in the time waveform. For example, broken or cracked gear teeth will show up at 1 times rotational speed in the spectrum, much like unbalance. The only way to distinguish the gear fault is by the impacting in the time waveform. Beat frequencies is another example. A beat frequency is created when 2 discrete frequencies very close together go in and out of phase. This can be clearly seen in the waveform, but will show up as one wide peak in a spectrum. It is important to collect good time waveform data because this is the foundation for the vibration spectrum and FFT analysis. A spectrum or FFT plot is a graphical representation of the individual discrete frequencies that make up a complex time waveform. The individual frequencies are displayed in a spectrum plot with amplitude information. A spectrum is created when a fast Fourier transform or FFT process is applied to a waveform. The FFT is a mathematical algorithm that calculates the frequency and amplitude of each discrete frequency in a complex time waveform. These discrete frequencies are then displayed together in a spectrum graph. Aliasing is a phenomenon that is specifically related to digitally sampled data. It occurs when the sample rate is not sufficiently higher than the highest frequencies present during the measurement. The effect of aliasing is that much higher frequencies manifest themselves at lower frequency events when sampled. This is a false or ghost data that can be very misleading. To avoid aliasing, most data collection systems employ anti-aliasing filters. Here we have an example of a 400 Hz Fmax spectrum with an 1152 Hz frequency also present. In the top example, we do not deploy anti-aliasing filters, and we get a ghost frequency at 128 Hz, as represented by the blue line. When we apply the anti-aliasing filters, as in the second example, this 128 Hz frequency is filtered out. Lines of resolution is the number of discrete bins or lines of data that will be created to display an FFT for a given frequency range. This is similar to the resolution of a television. With higher resolution, the greater the detail that can be displayed. The width of the bin is determined by the frequency range and the number of lines of resolution. A 0 to 100 Hz spectrum with 100 lines of resolution results in bins that are 1 Hz wide. In this example, you will notice that at 100 lines of resolution, all the frequencies are combined into one peak, represented by the red. If we increase the resolution to 3200 lines of resolution, we can see much more detail and can see two discrete frequencies closely spaced together. Windowing is a technique used to clean data to make it more usable. When the FFT process is performed with non-periodic events present, it can cause what is called leakage. This leakage is a result of the mathematical process applied and can be avoided by deploying windowing techniques. There are numerous windowing techniques. In the world of predictive maintenance, there are three that stand out: a Hanning, a rectangular or uniform window, or a flat top window. A Hanning window is the most commonly used window in vibration analysis. It is a good compromise between amplitude accuracy and frequency accuracy. There is up to a 16% variance in amplitude accuracy. A Hanning window is not very good for transient events such as non-repetitive impacts. Some leakage will occur with non-periodic events. A rectangular or uniform window is useful for transient events such as impact testing. This window has a very good frequency accuracy, but not as good of an amplitude accuracy, and can have up to a 36% variance in amplitude. A flat top window is very effective for things like balancing, where we have a very good amplitude accuracy with a variance of only up to 1%, and the frequency accuracy is not quite as good, but our primary interest is the amplitude, not the frequency. Averaging is a method used to remove fluctuations in the data from the spectrum, such as unwanted transient events. The more averages you use, the less fluctuation there will be. This can also improve your signal-to-noise ratio. The most common method is linear averaging. Overlap is a means of combining samples of data together to speed up the data acquisition process. To accomplish this, the last part of the data from a previous sample is used as the first part of the next sample. The final outcome is less unique data is being used, but faster data collection times. Many data collectors will allow the user to set the amount of overlap to use. In this example, we will first collect 4 samples or averages with no overlap. Each sample in this case will take 10 seconds to collect. The total time for collection is 40 seconds. Now let's use a 50% overlap. We will still get 4 samples, but in this case, the second, third, and fourth samples will use part of the data from the previous sample. Now our collection time is reduced to 25 seconds. There is a mathematical relationship between acceleration, velocity, and displacement that always holds true. Integration is used to convert from one unit of measurements to another. Acceleration is integrated to get velocity, velocity is integrated to get displacement, and acceleration to displacement requires double integration. Beware of double integration. Here is an example of what can happen with double integration. Notice the ski slope effect that is present in the lower data example. This is solely due to double integration. There are 2 ways to accomplish integration: using an analog circuit or by using a digital process. With an analog circuit, the integration is performed by hardware prior to sampling. The FFT is generated from the converted signal. This method yields an integrated time waveform as well, typically velocity. Using an analog circuit usually eliminates the ski slope effect. With a digital process, the signal is digitized and then converted or integrated mathematically. The FFT is then created from the converted signal. The time waveform will remain in the sensor units. This is why digital integration is often used. Phase is a measurement of vibration relative to a reference in time. The reference is usually an input from a tachometer. The vibration signal can then be compared to the tachometer signal, and the difference is measured to determine the phase. In this example, the tachometer input and the vibration signal will occur at the same phase angle. The red blade represents a heavy spot on the rotor. You can see how the vibration relates to the heavy spot on the rotor. When the heavy spot on the rotor is in line with the tachometer, the phase is 0 degrees. Since our tachometer stays in the same place, as the fan rotates, the heavy spot's phase shifts from 0 to 90 degrees to 180 degrees until we reach 0 again. Phase is what separates two events that occur at the same frequency. Phase is typically measured in degrees of rotation, from 0 to 360 degrees. In the example, we have two events that occur at the same frequency, but at a different phase. Cross-channel phase is a process where data is collected using two vibration channels simultaneously, and the phase difference between the two signals is derived. This type of measurement provides the phase difference between two measured points. Phase can be used for troubleshooting in the field using a tachometer or cross-channel phase. Phase is how we differentiate between problems that occur at the same frequency and can help determine the source of the vibration. Phase is used for balancing when a tachometer input is used. The amplitude and phase are measured, and the balance corrections are determined by the changes when a test weight is applied. There are several different types of specialty measurements, but the most common are HFD or high frequency detection, spike energy, enveloping, peak view, or shock pulse. HFD and spike energy are similar and are essentially overall measurements over a very broad frequency range that includes high frequencies that would not normally be captured. HFD is offered by several companies and generally measures between 5 to 20 kilohertz or 5 and 65 kilohertz. Spike energy will typically measure between 5 and 65 kilohertz and is expressed in GSE units. Enveloping and peak view work in very similar ways. Peak view is a proprietary process method created for CSI data collectors. The raw signal is filtered, rectified, and then enveloped. The result is a spectrum based on the enveloped signal. This is typically used to identify early bearing defects. The filter settings can have significant impact on the final data. Shock pulse is a signal processing technique originally developed by SPM that utilizes specially tuned sensors with a resonance between 32 and 36 kilohertz. The input signal is bandpass filtered, and then special processing is performed to derive two values, a carpet value and a max value. This measurement uses shaft diameter and equipment speed to normalize the readings. Shock pulse is the only method that will produce a severity indication as part of the process. You have just completed Module 3, Measurement Types. Please join us again for Module 4, Diagnostics Part A, which includes unbalance, misalignment, and gear-related problems. You can visit us at www.wilcoxon.com or call us directly at 1-800-WILCOXON.